Okay, hi everybody. So this is a fun one. Prove that Zn converges to Z if and only if the real parts converge to each other and the imaginary parts converge to each other. So first let's just remind ourselves what this sort of notation means. If Z is a complex number, then the real part of Z is this number here, and the imaginary part of Z is this length. So the real part of Z is the length of this segment, and the imaginary part of Z is the length of this segment. So Z is actually built out of the real part of Z plus I times the imaginary part of Z. Okay, so now let's learn how to prove something like this. Theorem. Zn converges to Z if and only if real part of Zn's converge to the real part of Z and the imaginary part of Zn's converge to the imaginary part of Z. Okay, so proof. First, we'd say there are two directions. We need to prove this way. We assume this and show that this holds. And we need to prove this way. We assume this and show this holds. Okay? So in math, the way you do this is you first just tell the reader that we're going to prove this direction first. So assume Zn goes to Z. We will show the real parts of the Zn go to the real parts of Z, and the imaginary parts of the Zn go to the imaginary parts of Z. And then blah, 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 blah. And when we're finally done with that piece, then we have to now, we're not done, because now we have to show this way. We're going to assume that both of these hold. Okay? We will show that that this holds. Oops. Okay, I could just easily write that. Okay, and then blah, 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 we have to prove that as well. And only once we've proved both directions of the if and only if are we done. Okay, so let's do, I don't know, let's just do one of them first. And so we have to replace this with something better. Okay. So we need to prove two things here. So first, we will prove real part of the Zn goes to real part of Z. So that means we need to look at real part of the Zn minus the real part of the Z. And we need to somehow show that it's less than D for any D, provided we go past some cutoff. And so how are we going to do that? Well, first let's do a little geometry here. So we have the Zn and the Z and the real parts and imaginary parts, and let's just look at a triangle. So if this is Z and this is Zn, then what we have is this triangle right here. Okay? And in particular, these coordinates, okay, and these coordinates are the real and imaginary parts. This is the real part of Zn. This is the real part of Z. This is the imaginary part of Zn. And the imaginary part of Z. So this is the length of Zn minus Z. This is the length of the imaginary part of Zn minus the imaginary part of Z. And this is the length of the real part of Zn minus the real part of Z. Okay? And for this first part, we're assuming that we know the Zn converges to Z, and we need to prove that these converge. So in other words, we need to show that this, let's take the real parts first. We need to show that this is going to be controlled by this, which we assume. Okay, so notice that basically, if we have Pythagorean theorem, if this length is a, and this length is b, then this length is c, and c squared is equal to b squared plus a squared. In particular, that means that that a squared is less than or equal to c squared, and that a is less than or equal to c, which is pretty obvious from this picture that this bottom piece is always going to be less than or equal to the length of this hypotenuse. But here's the proof, sort of starting from Pythagorean theorem. This is a positive number, b squared. The length of a side squared is positive, real number. And so if we get rid of a positive number, we've only made it smaller, possibly smaller. If b squared happened to be 0, we'd still have equals, but if b squared is positive, in general, this gets smaller. And also, by similar reasoning, b is less than or equal to c. And so basically, all of this, what's the conclusion? Real part of Zn minus real part of z is less than or equal to Zn minus c. And the imaginary part of Zn minus the imaginary part of z is less than or equal to Zn minus c. Okay, so maybe I'll just call this whole thing here star. So we need to prove this. Then I guess because since we assume that the Zn go to z, since the Zn go to z, we know that for any d, there exists a capital N such that going past that N implies Zn minus c is less than d. But star shows that the real part of Zn minus the real part of z, the size of that, will be less than or equal to Zn minus z, which is less than d. And so this means that the same capital N will work. So the same capital N works, so that real part of Zn converges to the real part of z. Similarly, the imaginary part of Zn converges to the imaginary part of z. Okay, so if we assume we have control over this, then we knew that some capital N existed that made this smaller. But by this very important diagram, and I guess really Pythagorean theorem, we actually knew that the real parts were smaller than this thing which we had control over, so the real parts were also small enough. And the same for the imaginary parts. So we are done with this proof with the crucial help of star. Okay. Now, this was basically Pythagorean theorem. It wasn't the triangle inequality. Now we're going to actually use the triangle inequality for the second part. Here we assume that these converge, and we need to show that this converges. So, for any d, a positive real number, we need to find capital N such that going past that cutoff implies that Zn minus z is less than d. Because that's what we need to show. Now, we can assume some control over these differences, and so that's going to help us. Now, calculating Zn minus z is just simply equal to, well, z is the real part of z plus I times the imaginary part of z. That's z. Zn is the real part of zn plus I times the imaginary part of zn. And then there's a subtraction sign. Okay. So I just sort of I zoomed into z and saw it has a real and imaginary part. I zoomed into z sub n, and it has a real and imaginary part. Okay, now I'm going to rearrange the real part of zn minus the real part of z, because that's exactly what I have control over. By my assumption, I'm assuming those converge, so I have control over this difference. And then plus I times, and I'm going to take the imaginary part of zn, and the minus the imaginary part of z. Now here is the triangle inequality. Now, how do I know that I can do this less than or equal? Well, so if this is A and this is B, then I have some complex number A, some complex number B, and I have their addition, A plus B, right? A plus B is here. That gives me a triangle. What triangle? This one. This has the length of A plus B. That's exactly this expression. But we know that any one side of a triangle is less than or equal to the size of the sum, or the sum of the sizes of the other sides. So this is the triangle inequality. Okay. Now look. We know that this converges, so we can make this as small as we like. In particular, we have two things, so maybe we can make it smaller than d over 2. For any d chosen, we can go over to this convergence and say, hey, set d, or I want d over 2 close. And they'll say, sure, there's a capital N1 that if you go past capital N1, you're good. And you're d over 2 close. Okay? This piece here, first of all, there's this annoying I, but remember, we can just do this. Because a complex number, you can just split up the sizes. The sizes multiply. And so the size of I is just 1. And so we basically just get, this is 1. So this line right here is equal to this line, because all I did is just notice that the I doesn't change the size. It just rotates, I just rotates this thing. It doesn't change the size at all. Okay. So now, okay, I will write, since the real parts of Zn go to real part of Z, there exists some N1 such that going past N1 implies the real part of Z, N minus real part of Z, is less than d over 2. I chose this desired closeness, so there is some cutoff that if I go far enough, I can have control on this. And since the imaginary parts converge, we assumed that, there exists some cutoff for them, where if you go past that cutoff, then the imaginary parts are smaller than whatever I want, and I'll choose d over 2. Why? Because d over 2 plus d over 2 will be equal to d. So I'm continuing like this thing is actually less than d over 2 over d over plus d over 2, which is d. And so at the end, I have Zn minus c less than d. Well, provided I'm past both of these, so choose capital N equal max of n1, n2, then n past capital N implies Zn minus Z is less than D by all of this, by all these calculations. And let's call this, I don't know, double star. And I'll just say this is all double star. Okay, so Zn actually does converge to Z, and we are done with the second half of the proof. Awesome. Okay, so triangles are pretty important because they have to do with distances. And this convergence, proving convergence is proving that things get really close. Close meaning distance. And so here we sort of use Pythagorean theorem and some fairly obvious things like this is always less, the blue here is less than the green, and the pink is less than the green. Here we use the triangle inequality, which says there are no shortcuts. This thing can only be shorter than going away and then back. And the details are sort of fun to figure out yourself. So try it now. See if you can prove both directions. We got this if and only if. That means we need to prove this direction and this direction. Make sure to help your reader. Make sure your reader knows what you're assuming and what you're going to prove at the various parts of your proof.